My name is Dylan Papazian, and this is my heat transfer project on the heat dissipation of rifle barrels. In the world of firearms and shooting sports, heat's generally something that you want to avoid as much as possible. Even a relatively small increase in heat can cause accuracy inconsistencies, like the shot stringing you see here. And in extreme cases, you can ruin the heat treat on steel components on the gun, or in like the worst case scenarios, you can even have catastrophic failures like the one shown here. So for this project, I compared the heat dissipation for two of my rifles. Rifle 1 is my Ruger American Predator with a matte blued finished medium weight barrel, and Rifle 2 is my Winchester Model 70 Featherweight with a polished blue barrel that has a lightweight contour. So to simplify the math for this problem, I approximated the barrel geometry as a simple cylinder. But since this problem is going to involve measuring temperatures over time, there's going to be an energy storage component, and any loss of that storage is going to either go to convection or radiation. So the problem itself is a pretty straightforward energy balance like this. Any energy lost in the storage is going to go through convection or radiation. And I did all the calculations per unit length. So any volume term becomes a cross-sectional area, and any surface area term becomes perimeter. And after I got all my values, I came back and calculated a BO number to see if I needed to redo all the math with transients in mind, but thankfully the BO number was very small, so lumped capacitance like this works just fine. All the properties of the air were evaluated at the film temperature in between the average barrel temperature and the ambient air temperature. So for the radiation portion of this problem, first step was to find the emissivity of each of the barrels. And that's not really something that manufacturers post on their websites, so that had to be found experimentally. It turns out the masking tape has a pretty well documented emissivity of 0.95, so I taped a portion of each barrel and left them in the same part of my living room for about 5 to 6 hours, just long enough for them to reach the same temperature. Then, using an infrared thermometer with an emissivity setting of 0.95, I measured the temperature of the tape. And then I moved to a bare section of the barrel and measured the temperature again, and I adjust the emissivity setting until the temperature of the bare section matched the temperature of the tape. So I did that for both barrels, and the emissivity of Rifle 1 came out to be 0.93, and the emissivity of Rifle 2 came out to be 0.78. For the final part of this experiment, I brought both rifles to the range, and I fired 10 rounds through each of them so that the barrels would get nice and hot. And then I measured an initial temperature, and then I waited 10 minutes and measured a final temperature at the same place in the barrel. And I made sure to measure the temperature at a place on the barrel where they were completely surrounded by air, so that you weren't getting any insulation from the stock or anything like that. And I left the rifle bolts closed during that 10 minutes so that internal convection wouldn't be a factor, and there would be a zero velocity, adiabatic condition for the air inside. I measured the ambient air temperature using my car's ambient temperature sensor. And there was a pretty steady breeze that day. It would die down occasionally, so I expected the convection coefficients to be somewhere between the standard values for free and forced convection, so somewhere around 25 watts per meter squared Kelvin. So the results were honestly a little surprising. Rifle 1, which is the rifle with the heavier barrel and the matte finish, actually dissipated 3.53% more heat than Rifle 2. And it looks like even though Rifle 2 lost more heat through convection, the finish on Rifle 1 allowed it to lose almost 70% more heat through radiation when compared to Rifle 2, which was just barely enough to push it into the lead, because these are relatively small values for the radiation compared to the convection. And looking at the convection coefficient values, Rifle 1 had a value of 20.2, placing it at the high end of free convection, and the convection coefficient for rifle 2 came in at 29.4, putting it at the low end of forced convection. What's interesting about this is this means that rifle 2 actually had better wind conditions for convection, and it still didn't dissipate as much heat. So while the barrel coating in this case appeared to be the deciding factor, convection accounts for way more of the total heat loss than radiation. So for a manufacturer, one way that they can try to exploit this would be to increase the barrel diameter. This will increase the heat loss through convection, or through increasing the surface area, but it will also increase the energy storage as you're getting a greater volume there too, and that means that the storage is actually going to increase more than your convection. So a good compromise to that is actually barrel fluting. You're increasing the surface area by adding these cuts in here. You're also saving weight by removing material, and the barrel itself is actually more rigid than a barrel of comparable weight. That's all. Thanks for watching.